Welcome to the 6th video in the Combinatorics series. Let's start off with a question. Usually I'd argue against just listing out all the things that you're trying to count, but in this example, it's not that bad. If x and y sum to 10, and they're each non-negative integers, which means they could be 0, importantly, then x can be 0, which means y would have to be 10, and x could be 1, which means y would have to be 9, and we can keep on listing it out until x equals 10, in which case y has to equal 0, and if you count that up, that is 11 solutions, so the answer is just 11. Let's try something a little bit harder. Now this problem's a little trickier than the last one because there's an additional variable z, and the variables sum to a bigger number 20. In both cases though, all of the variables are non-negative integers, meaning they're all greater than or equal to 0. Now, one solution that we can do is to divide and conquer the problem based on what one of the variables is equal to. So we can just arbitrarily choose x, and the smallest that x can be is 0, and in that case, y plus z would have to sum to 20, and the number of solutions for that is something that's similar to what we just counted in the last problem. So how many solutions are there for this? Well, y can equal 0 and z can equal 20, or y can equal 1 and z can equal 19, all the way up until y can equal 20 and z can equal 0. So that is 21 different solutions. So this case has 21 solutions associated with it. If x is equal to 1, well then, y plus z would have to equal 19. And how many solutions are there for this? Well, with the same logic we just used, we can deduce that there are going to be 20 solutions, so make sure you can do that on your own. And then for x equals 2, well, y plus z would have to equal 18, and there's going to be 19 solutions there, all the way down to when x is equal to 20, well then y and z both have to be 0, right? So there's only one solution there. So the answer to the question is just the sum of these cases, so that would be 1 plus 2 plus 3 all the way until 21. And if you know the formula for that, which maybe you do, maybe you don't, I can just tell you what it is. It's equal to 21 times 22 over 2, and maybe in a later video we'll prove that. But in this video, I want to show you a better way of doing this problem, and problems just like it. And now for the namesake of the video, an introduction to the powerful technique of stars and bars. So how does it work? Well, let's start with this first string of stars and bars. Is there some way of decoding this string into a solution that we are trying to count? Well, since there are no instructions for the decoding process, we can sort of give ourselves our own instructions. So one set of instructions we can use is to think of the two bars in this string as dividing the string into 3 regions, where the first region can correspond to x, and the number of stars in that region can correspond to the value of x. And similarly, between the two bars, we can say corresponds to y, and then to the right of the last bar corresponds to the variable z. So what would this string correspond to? What solution? Well, that looks like x equals 4, y equals 6, and z equals 10. Can you fill out the last 4? Well, this looks like x equals 20, since all the bars, or sorry, all the stars are to the left of the first bar, and it looks like y equals 0 and z equals 0. And this looks like x equals 1, y equals 18, and z equals 1. And this looks like x equals 6, y equals 0, and so z must equal 14, so there's 14 stars there must be. And this corresponds to x equals 18, y equals 2, and z equals 0. Interesting. But even more interesting is that if I gave you one of these solutions, you actually could map me back to this exact string, right? If I told you x equals 4, y equals 6, and z equals 10, you could have built this string. So this map actually goes both ways. There's a one-to-one correspondence between strings like this and solutions that we're trying to count. So we can count strings like this instead of the solutions, right? So what are strings like this, first of all? Like, what's going on here on this left side? So each of these are a string with 20 stars and 2 bars. So how many strings are there with 20 stars and 2 bars? That's basically counting binary strings with 20 of one character and 2 of another, which is something that we know already. That is just 22 choose 2 or 22 choose 20. We can just choose where to put the bars or where to put the stars in the string. And if we use the formula for what 22 choose 2 is, that's equal to 22 factorial over 20 factorial times 2 factorial, which everything cancels, and we get 22 times 21 over 2, which is exactly the same answer that we got before. But this is a much more powerful technique because it allows us to answer the question all at once with a simple 22 choose 2. Let's try another one. When the number of variables grows, and as their sum grows, the divide and conquer strategy gets more and more complicated, but the stars and bars approach scales quite nicely. So how many bars are we going to need in this problem? Well, the point of the bars is to serve as dividers to split this string up into different regions that correspond to the variables. So here we have 10 variables, so we need 10 regions. So how many bars do we need? Well, in the last question, we used 2 bars to get 1, 2, 3 regions. And notice that if I had 4 bars, I would have 1, 2, 3, 4, 5 regions. And so you should be convinced that the number of regions is 1 more than the number of bars, right? So even if you have 1 bar, for example, you already have 1, 2 regions, right? So if you want 10 regions, you need 9 bars. A common mistake is to think that you need 10 bars, so make sure you don't make that mistake. So you have 9 bars, and if each of the regions, the number of stars in them represents the value of that variable, and the variable sum to 100, well, of course, then that means that there should be 100 stars in total. So for this particular string in this order, what outcome do you think it corresponds to? Well, assuming that we're going to interpret the regions from left to right as representing x1 through x10 in that order, then it looks like x1 is equal to 100 because all of the stars are in the first region, and there's no stars anywhere else, which implies that all of the other variables are equal to 0. So this string maps to x1 equals 100, and x2 and x3 all the way to x10 are all equal to 0. Okay, and just to convince ourselves that the map goes in both directions, what if I gave you that solution, that all of the variables are equal to 10, x1 through x10, they're all equal to 10. What string does that map to? Well, of course we're going to need 9 bars and 100 stars, so 1, 2, 3, 4, 5, 6, 7, 8, 9. And that's going to give us 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 regions like we want. And we need 10 stars in each of these regions, right? So basically imagine that there's 10 stars here, 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 and 10 stars here. And that's the string that would map from and to this particular solution. So the answer to the question is the number of strings that there are like this, because this being 100 stars and 9 bars, because there's a one-to-one correspondence between such strings and solutions to the equation. And the answer is thus 109 choose 9. Now, to generalize this fully, let's say that instead that we were going from x1 to xk. So we don't know how many variables there are. And let's say instead that the sum is n, not 100. And all of the variables are still non-negative integers. How many solutions are there? Well, there should be k minus 1 bars and n stars. So in total, there should be n plus k minus 1 things in the string, or characters in the string, and k minus 1 of them are bars, so we can just choose where they go. So this, in general, is the answer to the question. Now, remember, it's really important that the variables are all non-negative integers. Sometimes that's not the case, and you have to adjust for that. Also, sometimes the problem comes in disguise. Okay, so let's take a look at an example like that. So here are the 8 identical marbles. And so for the first marble, there are 3 choices for friend. And no matter who you choose, there's 3 choices for the second marble. And no matter who you choose, there's 3 choices for this marble, all the way to the last marble, there's 3 choices. So to the multiplication rule, the answer seems to be 3 to the power 8. But that's not right. And can you figure out why? The reason is really subtle, because the question is not asking how many different ways are there to give out the marbles, which maybe it is 3 to the power 8. The question is asking how many distinguishable final outcomes are there. Those are different questions, and to see that, let's think about different ways of giving out these marbles. So maybe you give out the first 4 marbles to friend 1, and then maybe you give the next 3 marbles to friend 2, and then maybe you give the final marble to friend 3. So that's one of the 3 to the 8 different ways you could have given out the marbles, right? So that would be friend 1, friend 1, friend 1, friend 1, friend 2, friend 2, friend 2, friend 3. Now, a different way you could have given out the marbles is maybe you give the first marble to friend 3, and then maybe you give the next 2 marbles to friend 2, and then maybe you give the next 4 marbles to friend 1, and maybe you give the last marble to friend 2. So that's a different way of giving out the marbles, but it does not lead to a different or distinguishable final outcome. Since the marbles are identical, in both of these situations, friend 1 ends up with 4 marbles. And since they can't tell the marbles apart, they can't tell the outcomes apart. And so we want to count both of these distributions as one outcome. So 3 to the 8 would actually be overcounting. In both of these ways of distributing, friend 2 ends up with 3 marbles, and friend 3 ends up with 1 marble. So the only thing that really matters here, in terms of like what's distinguishable realities and not, is the number of marbles that each friend gets. They don't know which marbles they get, they just know how many marbles they get. So if we let x1 be the number of marbles that friend 1 gets, and x2 be the number of marbles that friend 2 gets, and x3 be the number of marbles that friend 3 gets, what do we know about x1, x2, and x3? Well, what do they sum to, for example? Well, they must sum to the total number of marbles, which should be 8. And then also notice that x1, x2, and x3, importantly, have to be non-negative integers, right? So they could be 0, for example, non-negative. So a solution to this equation actually corresponds to distinguishable distributions of marbles. So there's a one-to-one correspondence there between solutions to this equation and distinguishable final outcomes in our question. So we can count solutions to this equation, which we can use stars and bars for. And since there are 3 variables and they sum to 8, stars and bars tells us the answer to that is simply 10 choose 2. Now let's do this question with a little twist. Intuitively, since each friend requires at least 1 marble, we can start by just giving each friend a marble, and then we'd have 5 identical marbles left to distribute to the 3 friends. So the question would just reduce to how many distinguishable distributions are there of 5 identical marbles to 3 friends with no constraint at all. And that's a question that we just learned how to solve. But if intuitively that's not obvious to you, we can actually formalize that argument in the following way. So we want to count solutions to x1 plus x2 plus x3 is equal to 8 still, but the variables are no longer non-negative integers. They actually have to be positive integers now because of the fact that each friend must get at least 1 marble. So stars and bars requires that x1, x2, and x3 are greater than or equal to 0, but in this situation they're greater than or equal to 1. So how do we account for that? It's actually not so hard to do so. We can just define a variable y1 to equal x1 minus 1. And the reason we do that is because if x1 is greater than or equal to 1, then y1 would then have to be greater than or equal to 0. So we finally have the non-negative variable that we want, so we can use stars and bars, hopefully. So then y2 would have to be x2 minus 1, and y3 would have to be x3 minus 1. And then we can use this change of variables to rewrite our initial equation. So how would that look? So if y1 is x1 minus 1, then that means x1 is y1 plus 1. So x1 is y1 plus 1, plus x2 is y2 plus 1, and x3 is y3 plus 1, and that has to sum to 8. And so if we move all the 1s to the other side, we get y1 plus y2 plus y3 is equal to 5. And we're counting solutions for this equation such that each of the y's is a non-negative integer. So hopefully it's clear now why the question reduces to giving out 5 identical marbles to 3 friends. Of course, now we can use stars and bars. There's 3 variables which sum to 5, and that is simply 7 choose 2. Let's do the next question. We can try to divide and conquer this problem like we usually do, but I want to jump straight to the most elegant possible way of thinking about this question. So let x sub I be the number of times that I appears in your sequence of die rolls. So x sub 1, for example, is how many times you rolled a 1. So of course, if we add up all of the x's, like x sub 1 is the number of times you rolled a 1, x sub 2 is the number of times you rolled a 2, all the way up to the number of times you rolled a 20, which is the highest number you can roll, of course that should equal the total number of rolls that you rolled, which is equal to 5. So if you think about a particular solution to this equation, so let's think about this one. So x1 equals 1, x3 equals 1, x7 equals 1, x8 equals 1, x16 equals 1, and all the other x's are equal to 0. How many non-decreasing die roll sequences does that solution correspond to? Well, if you roll a 1, 3, 7, 8, and 16, the only way of rolling those numbers in a non-decreasing way is 1, 3, 7, 8, and 16 in that order. And similarly, if I gave you the sequence 1, 3, 7, 8, 16, you could have mapped it back to this particular solution to this equation. Let's do another example. So what if I gave you this solution? So x sub 12 is 3, x sub 18 is 1, x sub 20 is 1, and all the other x's are equal to 0. Well, that implies that there are 3 12s, 1 18, and a 20. And the only non-decreasing way of ordering those numbers is 12, 12, 12, 18, 20. And again, if I gave you that non-decreasing sequence, you could have mapped it back to this particular solution, which implies that there's a one-to-one correspondence between the non-decreasing sequences that we're trying to count and non-negative integer solutions to this equation. And that should have alarm bells going off in your head that this is stars and bars, right? So there's going to be 19 bars and 5 stars. So based on what we've already done, there should be 24 choose 19 unique solutions, which of course is equivalent to 24 choose 5. And that's also the answer to our question, which is kind of beautiful. Let's do another one. So we can use pink arrows to indicate which students are being selected. So this particular selection corresponds to choosing students 2, 5, 10, 14, 16, and 20. And none of those students are standing next to each other in line, so that is a valid choice. And notice that those 6 arrows divide the space up into 7 regions. And we can assign variables to those regions, and we can name those variables x1 through x7. Each of those variables represents how many students are in that region. So for example, x sub 3 represents how many students are in between the second and third selected student. So in this particular example, that would be 1, 2, 3, 4 students. So x sub 3 is equal to 4. Can you fill out the rest of these? I'll give you a second. So in this example, x1 is just counting person 1, so that's 1. x2 is counting 3 and 4, so that's 2. x4 is 3, x5 is 1, x6 is 3, and x7 is 1. Now, no matter how we place the pink arrows, what do we know for sure about the sum of the variables from x1 through x7? Well, if you think about the way we've designed those variables, when we add them together, they should give you all of the students that you have not chosen, right? So the pink arrows are pointing to the 6 students that you've chosen, and if there's 21 students in total, the remaining students, which is represented by the sum x1 through x7, should be equal to 15. Now, what else is true about each of these variables? Well, of course, they're all non-negative integers, right? Because you can't have fractional amounts of people or negative amounts of people. But are there any more constraints? Well, since the students cannot be standing next to each other, we can't have x sub 2 be 0. Because then these 2 pink arrows would be next to each other and we would have chosen 2 people that are sitting next to each other. So x sub 2, x sub 3, x sub 4, x sub 5, and x sub 6 all cannot be 0. But x sub 1, by the way, and x sub 7, those are fine. Like, those can be 0, because we can definitely choose, like, person 1, right? That's not a problem. So x1 and x7 are both greater than or equal to 0, so they're non-negative integers. But x2, x3, x4, x5, and x6 are actually all positive integers. Okay, so, but think about this. So this particular selection corresponds to one exact solution to this equation given these constraints. And that is exactly this solution. But also, if I gave you this particular solution to this equation with these constraints, you could have reverse engineered this selection of 6 students. So there's a one-to-one correspondence between selections of students that we are interested in and solutions to this equation such that x1 and x7 are non-negative integers and x2 through x6 are positive integers. So we can just count the number of solutions there are to this equation with these constraints. I'll give you a second to do that. So we want to count non-negative integer solutions to this equation with the additional constraint that x2 through x6 have to be greater than or equal to 1. The reason we want to do that is because the number of solutions there are to this equation with these constraints is the answer to our question, like we just talked about. So this greater than or equal to 1 thing is a little annoying, but we have dealt with it before. We can just define these new variables y2 through y6 that are equal to their respective versions of x minus 1. And that's going to allow us to rewrite this equation in terms of non-negative variables, which is the stars and bars condition. So if we just solve each of those equations for their respective x's and then substitute that here and then combine like terms and make sure you can do this on your own, you should get this equation. So notice that x1 and x7 are still the same because they were already greater than or equal to 0, but now we have this y2 through y6 stuff. And this other side has changed to 10. And we want to count non-negative integer solutions to this equation. That's the answer to our question. Luckily, now it's easy because it's a simple stars and bars application. There are 7 variables, so there should be 6 bars, and there should be 10 stars. So the total number of solutions, and hence the answer to our question, is simply 16, choose 6. Stars and bars is a wonderful method, and I hope it gives you as much joy as it has given me. See you next time.